Niacin's protective role in atherosclerosis reaches beyond lipid metabolism and into the cellular mechanics of immune survival, particularly in macrophages burdened by oxidized LDL, OXLDL. These immune cells, when overwhelmed by cholesterol and oxidative stress, undergo apoptosis, a form of programmed cell death that contributes to necrotic core formation and plaque instability in atherosclerotic lesions. The ability of niacin to counteract this apoptotic cascade introduces a powerful anti-atherosclerotic mechanism that works not by altering serum cholesterol, but by preserving the structural and immunological integrity of the plaque microenvironment. In OXLDL-loaded macrophages, niacin significantly reduces cell death through a series of intracellular events beginning with the activation of CD38. This enzyme catalyzes the formation of NAADP, a second messenger that induces calcium release from lysosomes via TRPML1 channels. The subsequent calcium signal promotes the expression of liver X receptor alpha, LXRA, a transcription factor that regulates genes crucial for cholesterol efflux and cellular stress responses, including Niemann-Pick C1, NPC1, ABCA1, and ABCG1. These proteins facilitate the removal of free cholesterol from lysosomes and the cell itself, reducing lipid overload, a primary trigger of apoptosis in foam cells. By relieving lysosomal cholesterol stress, niacin disrupts the proapoptotic feedback loop driven by cholesterol crystal formation, lysosomal membrane permeabilization, and cathepsin release into the cytoplasm. This reduction in lysosomal dysfunction helps preserve mitochondrial integrity, as damaged lysosomes often precipitate mitochondrial injury and activation of caspases. Niacin's ability to protect mitochondrial health indirectly supports ADP production, prevents cytochrome C release, and blocks the downstream activation of executioner caspases that drive apoptotic cell death. The anti-apoptotic benefits of niacin are not merely structural, they have important immunological consequences. Macrophages are central to the orchestration of inflammatory responses, efferocytosis, clearance of dead cells, and tissue repair. Preserving their viability in a lipid-rich, pro-oxidative environment of atherosclerotic plaques allows these cells to continue performing their regulatory and phagocytic functions. In contrast, widespread macrophage death not only weakens the immune response, but also leaves behind cellular debris and lipids that further fuel plaque inflammation and instability. Experimental data confirm these effects. Niacin-treated macrophages exposed to OXLDL show significantly lower rates of apoptosis, as measured by viability assays and reduced markers of cell death. These protective effects are lost when CD38 or LXRA is silenced, or when calcium signaling is inhibited, affirming the centrality of the CD38, NAP, TRPML1, LXRA axis in niacin's anti-apoptotic action. Moreover, niacin's suppression of IL-1 secretion in this same context suggests a dual benefit, preventing both inflammatory amplification and immune cell loss. This is critical because dying macrophages not only contribute to necrosis, but also release pro-inflammatory mediators that exacerbate local tissue damage and vascular dysfunction. Altogether, niacin's ability to preserve macrophage viability in the face of OXLDL stress reveals a potent cellular survival mechanism that underpins its broader anti-atherosclerotic activity. It protects against plaque destabilization by limiting necrotic core expansion, reducing inflammation, and maintaining immune surveillance. In a therapeutic context, this positions niacin as more than a lipid modulator. It becomes a guardian of immune cell function within the inflamed vascular wall, contributing to the long-term stability and regression of atherosclerotic lesions.